Section 3.6 is the chain rule. So the chain rule says, if f is differentiable at the point u equals g of x, and if g is differentiable at x, then the composite function f of g of x, which is the same, just two different notations, I prefer this one, I think, is differentiable at x, and the derivative of the composite function is the derivative of f prime, leaving gx alone, times the derivative of gx. In Leibniz's notation, different way of writing it, if y equals f of u and u equals g of x, then dy dx, our derivative, is dy du times du dx. That can also be written as dy du divided by dx du. So this is our derivative, change of y over change of x. Multiplying by the reciprocal, we get this, and the dy du's cancel out. So this all happens where dy du is evaluated at u being equal to g of x. So in other words, g of x is u, so we can call it f of u. Okay, with all that said, examples, derivatives of composite functions. So an object moves along the x-axis so that its position at any time is given by this function, which is a compositive function. Find the velocity of the function as a function of t. So velocity is the first derivative. So the first thing they do is they write s of t equals sine of 5t minus 3 as a composite. So s equals sine of u, and u equals 5t minus 3, our u substitution. So ds du, the derivative of s with respect to u, is cosine of u. Du dt, the derivative of u with respect to t, is 5. So using the chain rule, ds dt, which is what I'm looking for, the derivative of s with respect to t gives me my velocity. So I'm just going to multiply my ds du times my du dt, and then substituting my u back in, I get 5, and they put the 5 in front because it's a coefficient, 5 times the cosine of 5t minus 3. So that's using composite functions, breaking it down with the u substitution. We can also look at this as the outside-inside rule. And for simple functions, I think this is really an easy way to go. It helps you think about the chain rule as if y equals f of g of x, then dy dx is the derivative of the outside function, keep the inside the same, times the derivative of the inside. In other words, differentiate the outside and evaluate it at the inside, which is left alone, then multiply by the derivative of the inside. So if we do the one we were just looking at that way, we started with s of t equals sine of 5t minus 3. Sine is my outside function. 5t minus 3 is my inside function. So the derivative of the outside, the derivative of sine, is cosine, and we leave the inside alone, times the derivative of the inside. So 5 cosine of 5t minus 3. Just rewriting it with our coefficient in front. Okay? Now, here's another example of the inside-outside rule. So try this one on your own, pause the video, and then come back. So using the inside-outside rule here, rather than separating it to cos u and then u equals 3x to the 4th minus 2, we take the derivative of the outside, leave the inside alone, times the derivative of the inside. And then they clean it up a little bit. Okay, so pretty easy way to do the chain rule. You're used to this. It shouldn't be too big a surprise. Repeated use of the chain rule. There's more than one function here. So list from outside to inside, very inside. What are the functions we're looking at here? So the outside is the cube root of something. Inside of that is the sine of something. And inside of that is x squared. So I have three functions that I'm dealing with here. So let's take a look. We're going to start with the outside, which is our cube root. They rewrote it to the 1/3 power, which is helpful with cube roots, fourth roots, etc. We're going to take the derivative of the outside. That's our power rule, being the 1/3 down, raised to the 1/3 minus 1. Left the inside completely alone. The next thing I derivate is my sine, change that to cosine, leave that inside alone, and the last thing I derivate is my 2x. And then they'll probably clean it up, bringing the 2x to the front, so 2/3 x, sine x squared to the negative 2/3, cos x squared. So let's look at this with a parametrized curve, or parametric curve. So a parametrized curve is x of t comma y of t. It's differentiable at t if both x and y are also differentiable at t. So let's see how we can find dx dt, or excuse me, dy dx with a parametric curve. So dy dx is dy dt divided by dx dt. We can also write that as dy dx is dy dt times dt dx. So kind of similar to what we did on the other one. Remember that this is going to have to be the flip or the reciprocal of dx dt. Okay, so let's do an example with this. So find the tangent line to the parametric graph of x equals secant t and y equals tan t at the point where t equals pi over 4. Okay, so first thing I need is to know that dy dx is dy dt divided by dx dt. I'm going to leave it this way for now. And first of all, find out what is my dy dt and my dx dt. So off to the side. Dx dt is the derivative of secant t. So that's going to be secant t tan t. Dy dt is going to be the derivative of tan t, which is secant squared t. Neither of these are fractions, so I don't really need to worry about my reciprocal. I'm just going to put dy dt on the top and put dx dt on the bottom. And I can clearly simplify one of those. So I'm going to end up with secant t over tan t. And we could use it in that form. I think it might be easier to clean this up even a little bit more. We know that secant is 1 over cosine times tangent, but I need the reciprocal of tangent because I'm dividing by tangent, so multiplying by cos t over sine t, the reciprocal of tangent, and I end up with 1 over sine t, which we could even call cosecant t. So there's my dy dx. If I want the tangent line, I need two things. I need the slope, so I need dy dx evaluated at pi over 4, which is the cosecant of pi over 4, which is root 2. I also need an xy ordered pair. So let's go back to our original. X is going to be equal to the secant of pi over 4, which is root 2 also, just a coincidence. And y is going to be the tangent of pi over 4, which is 1. So I have the ordered pair, I'm running out of room here, root 2 comma 1, and a slope of root 2. So y equals slope times x minus root 2 plus 1. If I wanted to distribute that, root 2x minus 2 plus 1. So my final is root 2x minus 1. Okay, we'll do a few more of these on the homework, but that is it for the video.